Too big, too round, too weird. The moon exposed. What if I told you the moon isn't what it seems? It's not just a rock circling Earth. It's a cosmic oddity that breaks the usual patterns. Some of these details are well documented, like Apollo seismic readings and lunar rock chemistry. Others are unusual observations, and a few belong to contested interpretations and folklore. From its unusually large size to reports of it ringing like a bell when struck, the moon has scientists asking hard questions. Why does it appear exactly the same size as the sun from Earth? Could that be pure coincidence, or something more deliberate? And that brings us to one of its most unsettling traits. One of the most puzzling things about the moon is its geometric relationship with the sun as seen from Earth. During a total solar eclipse, the way the moon fits perfectly over the sun's disk is not an illusion we find everywhere. It's a geometric coincidence scientists note as striking. The sun's diameter is roughly 400 times that of the moon, and it is also about 400 times farther from Earth. This near-perfect ratio is why, from our perspective, they appear almost exactly the same size in the sky. No other major moon in our solar system plays the same stabilizing role with such a close geometric match to the sun from its planet's vantage point. To see how unusual this is, compare it to other worlds. On Jupiter, moons like Ganymede or Callisto appear as tiny dots sliding across the sun. On Mars, its misshapen moons can only partially cover the sun, producing irregular shadows. For Earth, the alignment is so exact that even a small change would break it, shift the moon's distance by just 5% in either direction, and total eclipses, as we know them, would vanish. Some researchers consider this a lucky outcome of orbital mechanics. Others view it as a clue that something about our moon is unlike any other. Beyond its orbital placement, its composition tells another story. Scientists note lunar rocks from Apollo missions share nearly identical oxygen isotope ratios with Earth rocks, a surprising match that complicates theories of the moon forming from foreign material. This data point continues to be one of the most persistent challenges to conventional models. The moon's scale in relation to Earth is just as striking. Most moons are far smaller in proportion to their planets. Jupiter's giant Ganymede is only about 4% of Jupiter's mass, while our moon is roughly 1.2% of Earth's mass, about 1/81st the mass of its host. This size is sufficient to keep Earth's axial tilt steady over geological timescales, helping maintain a relatively stable climate that could be crucial for life. Taken together, these geometrical and compositional qualities suggest a complicated origin, perhaps more complicated than standard explanations allow. And that invites a closer look at the prevailing theory for where the moon came from and whether it holds up under scrutiny. The leading scientific model holds that an oblique collision with a Mars-sized body, often called Theia, early in Earth's history ejected material into orbit that later combined to form the moon. This hypothesis accounts for the moon's relative size and orbital behaviour, but certain findings make the picture more complicated. One major challenge is the isotopic evidence. Apollo samples revealed that lunar rocks share nearly identical oxygen isotope ratios with Earth's, something difficult to explain if much of the moon's material came from a separate body. Because oxygen isotopes in lunar and terrestrial rocks are nearly identical, some researchers say Theia would have had to share an unusually similar composition to Earth, or else the post-impact mixing must have been nearly complete. Both scenarios are tricky to reconcile with straightforward versions of the impact model. Simulations of the giant impact also struggle to reproduce some details of the actual Earth-Moon system. Angular momentum and composition remain two of the hardest constraints to match. Chemical differences present another puzzle. The moon's mantle appears poorer in iron than expected if it came largely from Earth's mantle. It also has reduced amounts of certain volatile elements, again suggesting aspects of its formation we may not fully grasp. These mismatches hint that the processes shaping the moon may have been more complex than a single clean impact. Then there's the seismic evidence from Apollo-era impacts. NASA intentionally crashed spacecraft modules into the moon to study its interior. Seismic records show the Apollo 12 lunar module impact produced reverberations lasting about an hour. And another impact during Apollo operations generated echoes measured at over 3 hours. Scientists described it as ringing like a bell, striking for a body thought to be solid rock. While this does not in itself prove unusual structure, it adds another layer to the uncertainties. Either the impact models are incomplete, or there are properties of the moon's interior and history we don't yet understand. And when you add up these anomalies, the composition, the density, the seismic behavior, they begin to suggest possibilities that at first sound improbable, yet have still drawn the attention of serious investigators. Among the more unconventional ideas to explain the moon's quirks is the hollow moon hypothesis, a suggestion from some researchers and commentators that its interior might be less solid than assumed. This view often points to Apollo-era seismic data. When astronauts deliberately crashed equipment into the surface, the seismic stations left behind recorded vibrations lasting far longer than similar impacts on Earth. Instead of fading within minutes, the signals persisted for an hour or more. Scientists generally interpret this as evidence for strong scattering within a highly fractured outer layer, or megaregolith, and possibly an unusual internal structure, but not direct proof of emptiness. The data are real. The interpretation remains open to debate. Conspiracy discussions also highlight certain photographic anomalies. In Apollo imagery and telescope observations, objects dubbed the Shard and the Tower appear to rise sharply from the surface, some with seemingly geometric outlines. Mainstream explanations suggest lighting, shadow effects, perspective, or camera artifacts as the likeliest causes, and emphasize that such images are ambiguous without confirmation from multiple independent high-quality data sets. Another long-standing curiosity is transient lunar phenomena, brief flashes, glows, or coloured lights observed for centuries in craters such as Plato. Astronomers, including Barbara Middlehurst, have catalogued hundreds to nearly 2,000 such reports. While meteor impacts, outgassing, or visual effects may account for some, their persistence in the observational record keeps them at the topic of scientific and amateur interest alike. Modern mapping has also revealed definite subsurface voids. Orbital imaging from missions like LRO and Japan's Kaguya has identified skylight pits and likely entrances to lava tubes, such as those in the Marius Hills region. These openings, tens to over 100 metres wide and extending perhaps 170 metres deep, confirm that significant underground cavities exist, features that could explain certain seismic or gravitational anomalies without invoking a hollow shell. Natural explanations, from fractured megaregolith to lava tubes and uneven density, can account for aspects of what we observe. Still, several features remain scientifically interesting and worth further mapping. And in the realm of unexplained features, one characteristic of the moon stands out for its measurable, real-world impact: the surprising irregularities in its gravitational pull. Lunar orbiter tracking in the 1960s revealed something unexpected. The moon's gravitational field is uneven, with certain regions exerting a stronger pull than others. These areas, known as mass concentrations or mascons, were important for Apollo planning because they could subtly alter the path of orbiters and landers. Without accounting for them, spacecraft could drift off course, forcing mid-flight corrections to hit targeted landing sites. Later, Apollo missions confirmed the effect firsthand when crewed modules experienced small but measurable tugs during descent. Mascons are often located beneath large circular planes like Mare Imbrium and Mare Serenitatis. The leading natural explanation is that enormous asteroid impacts billions of years ago created these basins with later mantle uplift and lava fill concentrating dense material underneath. However, High-resolution mapping from NASA's Grail mission revealed patterns and mismatches that simple impact and fill models struggle to fully explain. In some cases, the densest spots don't line up exactly with the visible basin, and the strength of the anomalies is greater than predicted by earlier simulations. Mass cons complicate formation models. They don't prove a non-natural origin, but they are a persistent structural puzzle that any origin scenario needs to account for. Which explanation sounds more plausible to you? Violent early impacts rearranging dense material, or something else entirely? Let me know in the comments and explain why. Some researchers suggest these anomalies might hold clues about the moon's deep structure, possibly relating to unexpected core composition or remnants from the hypothetical Theia impactor. Others propose that the moon's interior could be more varied than previously thought, with patches of unusually dense rock or metal persisting for billions of years. What's striking is that such features have endured despite geological processes that might have evened them out over time. Upcoming missions equipped with more sensitive gravimeters aim to map these variations in greater detail, seeking to reveal whether mass cons are simply frozen records of ancient impacts or signs of something far less understood. In either case, they are one more element adding to the moon's already complex story, a story that continues to challenge straightforward answers and pull us toward deeper questions about our nearest neighbour. The moon isn't just a familiar sight in our sky. It's a subject full of unresolved questions that continue to invite investigation. Consider these standout clues. Apollo seismic echoes lasting for hours, the near-identical oxygen isotopes in Earth and Moon rocks, the mass cons and gravity anomalies mapped by Lunar Orbiter and Grail, and the lava tube skylight pits revealed by LRO. These anomalies raise deep questions. Some invite natural explanations, others encourage speculation about more directed causes. Which fits best depends on which data you trust most. Share which moon mystery you find most compelling in the comments, and subscribe for more explorations. Look up with fresh curiosity. The moon may be an old friend, but it still keeps secrets. Heaps.